Ciao, amici tensori. Hello, tensor friends. Uh, in my studies, I ran across something I did not know. Relative tensor. What is a relative tensor? Just when you think you're getting this stuff nailed down, they come up with something new. No, it's not new. It's just new to me. Okay, let me see if I can explain it, and that will determine if I understand it. So be sure and jump in. Okay, let's start with the Jacobian determinant because we've seen that before. Okay, if a object transforms like this, then it is a tensor, right? So we have the basis vector in the prime, the system, times the Jacobian with I prime, times the basis vector in the unprime, the system. So if this is true, then this is a tensor. That's the way it's done. Now, this Jacobian here can also be expressed as a matrix, and it would have as many entries as you have dimensions. So if you have two dimensions, this would be a 2 by 2. In three dimensions, a 3 by 3, etc. Right? So let's do an example. Cartesian to polar, okay, where we have x equal r cosine theta and y equals r sine theta. All right, so here's what our matrix would look like. So the the top ones go by convention go on across the top, twos here. The bottom ones are the ones and twos this way. Okay, so this is xr, which is a partial x partial r, is cosine the theta, etc., etc., etc. We've done this many, many times. Okay. Now, algebraically, we would write this like this. So er is equal to this operator basis vector, this operator basis vector. So these are vectors. So this can be expressed as a column vector, and that can be expressed as a column vector, right? So it would look like this. So this is er, and this is e theta. So now we can take the determinant of this. And so it's this times this minus that times that. So it'd be r cosine the theta minus a minus is a plus, r sine theta. You factor out a r, cosine squared theta plus sine squared theta is equal to 1. So it's just r. Okay? Now, we got that under our belt. Let's take a look at the metric tensor, Gij, for polar coordinates. Okay? And we've seen this also many times. GRR is 1, 0, 0. G theta theta is r squared. Now, what's the determinant of that? It's r squared. Now, excuse me, there's a cat on my head. If G, so G is equal to the determinant of Gij. If G is a tensor, then it transforms like this, right? So it has two indices here. For every index, you need a Jacobian, and here is your unprimed, right? So we know this is a tensor. The metric tensor is a tensor. We know that. Now, is its determinant a tensor? So we would take the determinant of both sides. And remember from linear algebra, the determinant of a product, so this is a product, can be expressed as the product of the determinants, right? So this can become this. Now, this is just G prime, and this is just G, so let's write it like this. Now, what's the determinant of this and the determinant of this? Well, those are the same thing, right? So it's just J squared. It just looks like this. So we got G prime is equal to J squared G. Now, the determinant of a metric tensor is an example of a relative tensor or tensor density. You see this in literature also. I think this is the modern terminology, and this is the terminology as an example that's in my book, Absolute Differential, the Calculus by Levi-Civita. And this is with a weight of 2. So the weight means what is this exponent of the Jacobian, right? So let's do an example, right? So here's what we have. So G prime in polar is r squared. G in Cartesian, because we went from Cartesian to polar, right? So the Jacobian in Cartesian to polar is just r. So r squared equals r squared and 1. That's a true statement. So that's how that works. So the tensors we've been studying, we've been using are called absolute the tensors, and they're a special case of relative tensors. So, who knew? So let's just take a tensor like this. Uh, it has two free indexes, so it needs two Jacobians, and here's the system. Well, out in front of every tensor we've been using, and we didn't know this, or I didn't know this, I should say. No, 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 is there is the Jacobian with this exponent w. And in the case of a tensor, an absolute tensor, the ones we've been using, this is zero. So j to the zero is one. So it's always there. We just don't ever see it. And then you get to something like this, and you find out it's not a tensor because it has a exponent. So if w is equal to zero, this tensor is called absolute. If w is not equal to zero, this tensor is called relative. And so this opens up a whole new world of tensors, and they show up in textbooks, even in general relativity, the textbooks. So I thought that was really interesting, and I'm glad I took the time to do it. All right, see you later.